I hope you've seen my previous video on PEM and phosphoric acid fuel cells. The next type of fuel cell I want to discuss are molten carbonate fuel cells. A molten carbonate fuel cell, or MCFC, is a high-temperature fuel cell that uses molten carbonate as the electrolyte. The molten carbonate is embedded in a ceramic aluminum matrix made up of a lithium aluminum oxide, or LiAlO2. The aluminum matrix is supported by a nichrome wire mesh so that the molten carbonate paste stays in place even if oriented in an odd direction. The transfer ions in an MCFC are carbonate ions, CO3 double negative. The carbonate electrolyte material can be potassium carbonate or sodium carbonate or lithium carbonate or a mixture of all three carbonates depending on the manufacturer's recipe. The melting temperatures of potassium carbonate and sodium carbonate are 890 degrees Celsius and 850 degrees Celsius respectively. Temperatures above 500 degrees Celsius are high enough to soften the carbonate electrolyte sufficiently to allow ion migration. Temperatures above 700 degrees Celsius may cause premature evaporation of the carbonate electrolyte. So MCFCs operate best in the 550 to 700 degrees Celsius temperature range. This is a high temperature compared to PEM and phosphoric acid fuel cells that operate at 90 degrees Celsius and 180 degrees Celsius respectively. The high temperature of MCFCs allows the use of non-platinum catalysts. MCFCs have both reforming catalysts and transfer reaction catalysts. Nickel and chromium can be used as catalysts in both reformers and in the transfer layers. Nickel and chromium are far less expensive than the platinum catalyst used in low-temperature fuel cells such as PEM fuel cells. The use of less expensive catalysts in molten carbonate fuel cells allow them to produce much more power for much less material cost than PEM fuel cells or other low-temperature fuel cells. Other economics of MCFCs promote economy of scale, bigger is better. MCFCs are used as stationary power plants rather than vehicle-borne mobile fuel cells. MCFCs are produced commercially in power ratings starting at 300 kilowatts and up to multi-stack MCFCs power plants rated at over 5 megawatts. A 5 megawatt plant can power a large factory or a small town of up to 5,000 homes. Another benefit of high-temperature fuel cells is that they can be built with internal reformers that can reform methane and steam directly into hydrogen. Engineers can take advantage of the endothermic or heat-absorber reaction of reforming methane and steam into hydrogen fuel inside the fuel cell stack. They can use the endothermic reaction to cool the MCFC stack directly rather than having to pump in coolant from an external source. Sulfur will poison the catalyst. The nickel-chromium-based catalysts are not poisoned by carbon dioxide or carbon monoxide. In fact, CO2 is a necessary component of the cathode gas, as it is used to make the carbonate ions that are the transfer ions through the carbonate electrolyte. It is preferable to use methane as fuel rather than more complex hydrocarbons such as propane, as longer-chain hydrocarbons can deposit carbon on the reformer catalyst. In most MCFCs, the internal reformer catalyst is not replaceable. Some FCFC systems use a dual system of internal and external reformers. The external reformer catalyst can be replaced and serves as a fuel filter to absorb sulfur and more complex hydrocarbons. So, only methane and steam will be able to get into the internal reformer. The excess heat from a molten carbonate fuel cells can be used for a variety of cogeneration purposes, including heating homes or nearby buildings. A cogeneration system can be also called combined heat and power or a CHP system. The excess heat from MCFCs have been used for industrial purposes, including heating furnaces for chemical processing and even heating ovens to bake bread in a bread factory. The excess heat from an MCFC has also been used to power a small turbine electric generator, so forming a hybrid system. In the hybrid system, the MCFC creates part of the electricity and the turbine generator produces part of the electricity. By itself, an MCFC has an efficiency of over 47%. When paired with a cogeneration heating system or a secondary electric generator like the turbine electric generator, a hybrid MCFC CHP system could have an efficiency between 60 and 80%. MCFCs can use methane drawn straight from natural gas pipelines. Natural gas can be more than 90% methane. There should be a filtration system to absorb sulfur and more complex hydrocarbons in place between the gas pipeline and the MCFC power plant. This filtration system could be a sacrificial external steam reformer. Other good sources of methane could be biomass such as garbage, food waste, or sewage that is processed into methane in a biodigester. The use of biomass as a methane source is very green as the carbon in the biomass is already part of the carbon cycle. Fossil fuels other than natural gas, such as diesel fuel and coal, can be processed into methane that can be used in MCFCs. Another source of fuel could be syngas, the synthetic gas waste product of many chemical processes that contain methane, hydrogen, and other hydrocarbons that can be reformed into fuel for the molten carbonate fuel cell. The downside of high-temperature fuel cells, including MCFCs and SOFCs, is seals and gaskets. These high-temperature applications require metal-on-metal seals or ceramic gaskets. Rubber and plastic gaskets melt at temperatures seen in MCFCs and SOFCs. The problem with metal-on-metal seals is that they warp and then leak. Ceramic gaskets are prone to crack formation and leaks. Ceramic gaskets are too brittle to use in automobiles and other vehicles that are subject to vibration or high acceleration loads. MCFCs are limited to stationary uses only. MCFCs are also prone to degradation. Catalysts age or get poisoned beyond usefulness after as little as 5 years of operation. After 7 years, the corrosive effect of molten carbonate vapors and high-temperature steam can degrade the cathodes, and even cause high-grade stainless steel structural components to rust beyond the point where the MCFC needs to be retired. In operation, the molten carbonate fuel cell cycle starts with the heating of the fuel to operating temperature, usually done by means of a heat exchanger through which the MCFC fuel pipes are heated by its own exhaust gases. Steam is added to the heated fuel to help the hydrogen reforming process. In the hydrogen reformer, methane gas and steam are reformed into hydrogen, H2, and carbon dioxide, CO2. The reforming reaction is shown. CH4 plus 2H2O reacts to form 4H2s plus 1 CO2. The heat absorbed in the reaction is 165 kilojoules per mole. The reforming reaction is endothermic. It absorbs heat. The reformer is an indirect internal reformer. This indirect internal reformer, or IIR unit, is a thin panel placed within the fuel cell stack. The indirect internal reformer unit has 3 or 4 cells above it and 3 or 4 fuel cells below it. This internal reformer unit serves to cool the fuel cells above it and below it, much like the internal cooling layer of a PEM fuel cell stack. Not all the methane is reformed in the IIR. The mix of methane fuel and steam and newly formed hydrogen is piped from the reformer unit into the anode space of the fuel cell. There is more reforming catalyst within the anode to provide more cooling through direct internal reforming, or DIR. Once the hydrogen is in the anode space, it is exposed to transfer reaction catalyst in the transfer layer next to the electrolyte. In the transfer layer, carbonate ions are coming up from the cathode through the electrolyte. In the anode transfer catalyst layer, the catalyst causes the anode half-cell reaction. H2 and CO3 double negative ions react into water, H2O, and carbon dioxide, CO2. In reacting with the hydrogen, the carbonate ion releases the 2 electrons that each carbonate ion carries. The released electrons move into the anode current collector, ACC, and out into the wire through the anode terminal. As written, the anode half-cell reaction releases 8 electrons. The electrons are captured by the anode current collector and are drawn into the wire circuit through the load and into the cathode current collector through the cathode terminal. Not all the hydrogen fuel is used up in the anode. Some H2 is allowed to slip into the anode exhaust. This hydrogen slip is allowed to ensure that the entire anode surface can participate in the anode reaction and electricity production. Even methane is allowed to slip the anode. The anode exhaust contains H2O, CO2, H2, and CH4. This anode exhaust is sent through a combustor where an overabundance of air is used to burn up the H2 and CH4 into more H2O and CO2. The combustion process heats the air, steam, and carbon dioxide to a high enough temperature to flow directly from the combustor into the cathode. The combustion exhaust gas enters the cathode as O2, N2, H2O, and CO2. Once the combustion gas is in the cathode catalyst layer helps the O2, CO2, and electrons that travel the wire circuit from anode to cathode to react to form carbonate ions that can enter the molten carbonate electrolyte, ready to travel back to the anode side and repeat the cycle. The cathode half-cell reaction is shown. 4 O2s plus 4 CO2s plus 8 electrons react to form 4 carbonate ions. The leftover air, steam, and carbon dioxide can be exhausted from the cathode into the atmosphere. On its way out the exhaust pipe, the excess heat from the cathode exhaust can be recovered in a heat exchanger or heat recovery unit, HRU. The heat can be used to preheat incoming fuel, or it can be used in cogeneration or combined heat and power CHP process, such as heating buildings or turning a secondary turbine electric generator. The molten carbonate fuel cell alone has an electrical efficiency exceeding 47%. This raw efficiency compares with the PEM or phosphoric acid fuel cell efficiencies. When an MCFC is used in a CHP system, the CHP system can have an efficiency in the 60 to 80% range. Low-temperature fuel cells like PEM fuel cells cannot compete with high-temperature fuel cells like molten carbonate fuel cells or solid oxide fuel cells as stationary power plants inside a CHP system. In the figure, I show the operation of a single molten carbonate fuel cell. In the second figure, I have a diagram showing a section of an MCFC stack with an indirect internal reformer, IIR, sandwiched between 6 fuel cells. The diagram shows the H2O and CH4 fuel entering the IIR reformer, then the H2 and CO2 leaving the IIR reformer, then the H2 and CO2 entering the anode, then the CO2 and H2O leaving the anode, the air, O2, CO2 entering the cathode, and the CO2 and H2O exhaust leaving the cathode. The 6 fuel cell stack shown on the figure is a repeating unit. This IIR reformer-centered unit is repeated a dozen times to build an MCFC fuel cell stack, hundreds of fuel cells tall. The fuel and air can flow through the anode and cathode in cross-flow, co-flow, or counterflow configurations. Cross-flow is the most common flow pattern. Cross-flow is where the air in the cathode flows in a direction perpendicular to the fuel flow in the anode. Each molten carbonate fuel cell has a voltage difference across of about 1 volt between anode and cathode. By stacking hundreds of fuel cells in series, the terminals at both ends have differences of hundreds of volts between them. The whole fuel cell stack is clamped together by compression plates at both ends. The entire stack is enclosed in a sealed vessel with air and fuel pipe leading in and exhaust pipe leading out to carry away the CO2, H2O, and excess heat. The excess heat could be extracted by a heat exchanger or heat recovery unit for use in a combined heat and power system. The MCFC system diagram shows the natural gas fuel and steam being mixed as flows into the sulfur filter. The methane steam mix is preheated by the gas in the heat recovery unit, HRU. The preheated fuel is pumped into the indirect internal reformers, or IIR, of the fuel cell stack. The IIR reforms the methane and steam into hydrogen gas and CO2. The electrochemical reaction occurs across the electrolyte between the anode and the cathode. The anode gas exhausts into the anode out manifold. The anode out gases go through the combustor where they are burned with an overabundance of air to add O2. The O2 and CO2 gases enter the cathode inlet manifold where the gases are distributed to the stacked cathodes. The hot exhaust from the cathode out manifold is sent to the heat recovery unit to exchange its heat with the CHP system before it is exhausted as CO2 and steam. Major manufacturers of molten carbonate fuel cells include MTU of Germany and Fuel Cell Energy, or FCE, based in Connecticut, USA. Another high-temperature fuel cell is the SOFC, or Solid Oxide fuel cell. An SOFC uses a ceramic electrolyte embedded with materials that could include urea-stabilized zirconia, or YSZ. Scandia-stabilized zirconia, or SCSZ. And lastly, gadolinium-doped ceria, or GDC. Zirconia is zirconium dioxide, ZrO2. Ceria is cerium-4 oxide, or CeO2. Both oxides promote the migration of oxide ions at high temperatures. The transfer ions in an SOFC are oxide ions, O double negative. SOFCs can operate at higher temperatures than molten carbonate fuel cells. MCFCs must operate at temperatures below 700 degrees Celsius due to electrolyte evaporation. SOFCs can operate at temperatures as high as 1000 degrees Celsius. SOFCs typically operate in the 800 degrees Celsius to 1000 degrees Celsius temperature range. This is a high temperature compared to PEM and phosphoric acid fuel cells that operate at 90 Celsius and 180 Celsius respectively. The high temperatures of SOFCs allow the use of non-platinum catalysts. SOFCs have both reforming catalyst and transfer reaction catalyst. Nickel can be used as catalyst in both reformers and in the transfer layers. Perovskites, which are calcium titanium oxides, have been used as catalyst. Nickel and perovskites are far less expensive than the platinum catalyst used in low-temperature fuel cells such as PEM fuel cells. Less expensive catalysts in solid oxide fuel cells allow them to produce more power for less material cost than PEM fuel cells or other low-temperature fuel cells. Low-temperature PEM fuel cells are able to use rubber gaskets. PEM fuel cells are currently being used to power automobiles and forklifts. The high-temperature SOFCs must use ceramic gaskets or metal-on-metal seals. Melted glass seals have been tried on SOFCs. Glass seals and ceramic gaskets are brittle and subject to cracking. Metal-on-metal seals can warp and leak. These leak-prone gaskets are not suitable for use in vehicles. So, SOFCs are better used in stationary power plants. The gasket issue was not dissuading transportation companies from doing research to develop SOFCs for use in vehicles. An SOFC could be isolated from vibrations and jolts with shock absorbers. Another problem with high-temperature fuel cells is long startup times. PEM fuel cells come up to operating temperature in seconds. SOFCs and MCFCs take hours to reach operating temperature. Among companies doing SOFC research include Rolls-Royce, BMW, Siemens, and Fuel Cell Energy. Like other high-temperature fuel cells, SOFCs can be built with internal reformers that reform methane and steam directly into hydrogen. Engineers can take advantage of the endothermic reformer reaction to cool the SOFC fuel cell stack rather than having to pump in coolant from an external source. SOFC catalysts are subject to sulfur poisoning. Sulfur filters must be put in line with uncertain fuel sources. The excess heat from SOFCs can be used to heat buildings and in other cogeneration and combined heat and power CHP systems, including hybrid systems involving secondary turbines to turn an electric generator. SOFCs can have electrical efficiencies over 50%. When paired with a cogeneration or CHP system, the SOFC hybrid system could have an efficiency between 60 and 80%. In operation, the solid oxide fuel cell cycle starts with heating the fuel to operating temperature. The incoming fuel can be heated with a heat exchanger using the SOFC's own exhaust gases. If the SOFC has an internal reformer, the methane gas and steam are reformed into hydrogen and carbon dioxide. The reforming reaction is shown. The reforming reaction absorbs 165 kilojoules per mole of product. The reforming reaction is endothermic and can be used to cool the SOFC stack. The steam, CO2, and newly formed hydrogen is piped into the anode space of the fuel cell. Once the hydrogen is in the anode space, it is exposed to the transfer reaction catalyst in the transfer layer next to the electrolyte. In the transfer layer, oxide ions are coming up through the electrolyte. The anode transfer catalyst causes the anode half-cell reaction, and H2 and O double negative ions react into water, H2O. In reacting with the hydrogen, The oxide ion releases its 2 electrons into the anode current collector and out into the wire through the anode terminal. The SOFC anode half-cell reaction is shown. 2H2 plus 2O double negative react to form 2 H2Os plus 4 electrons. The electrons released into the anode current collector are drawn into the wire circuit through the load and enter the cathode current collector through the cathode terminal. In the cathode half cell, the cathode catalyst layer helps the O2 and the electrons react to form oxide ions. The oxide ions, O double negative, enter the electrolyte ready to travel back to the anode side and repeat the cycle. The cathode half cell reaction is shown. O2 plus 4 electrons react to form 2O double negative. The leftover air, steam, and the carbon dioxide can be exhausted from the cathode into the atmosphere. On its way out the exhaust pipe, the excess heat from the cathode exhaust can be recovered in a heat exchanger or a heat recovery unit, HRU. The excess heat can be used to preheat the incoming fuel. The excess heat recovered by the HRU can be used in cogeneration or in a combined heat and power process such as heating buildings or turning a secondary turbine electric generator. In the figure, I show a diagram of the operation of a single solid oxide fuel cell. The fuel, H2, comes into the anode. Air, O2, comes into the cathode. Oxide ions traverse the electrolyte to react with the hydrogen fuel in the anode to produce water, H2O. Electrons released in the anode reaction travel the circuit into the cathode where new oxide ions are dissociated from the air. Waste products are exhausted from the cathode. The voltage across the terminals of a single solid oxide fuel cell is about 1 volt. The single solid oxide fuel cells are stacked in a similar fashion to that of a molten carbonate fuel cell, including the internal reformer unit for every 6 to 8 fuel cells. An SOFC stack of several hundred fuel cells will result in a combined voltage difference of several hundred volts across the whole stack. In the figure, I show a reformer unit sandwiched between 6 fuel cells. The diagram shows the H2O plus CH4 fuel entering the IIR reformer. The H2O and CO2 leave the IIR reformer and enter the anode. The air, which is made up of O2, CO2, and H2O, enter the cathode. The CO2 and H2O exhaust leave the cathode. The nitrogen in the air is inert and not shown. The reformer in 6 fuel cells is a repeating unit that can be stacked dozens of times to create an SOFC stack of several hundred cells. In both solid oxide and molten carbonate fuel cells, new water is formed in the anode. The MCFC uses carbonate ions as the transfer ion to react in the anode with H2 to make H2O plus CO2 plus electrons. The SOFC uses oxide ions as the transfer ion to react in the anode with the H2 to make H2O plus electrons. Technically, the SOFC does not need CO2 to function. Practically, the SOFC will produce CO2 as a result of the reforming reaction of methane and steam into H2 plus CO2. If hydrogen gas, H2, is available to the SOFC from a carbon-free or non-fossil fuel source, the waste from the SOFC will be only steam, H2O. An SOFC by itself has an electrical efficiency greater than 50%. An SOFC exceeds PEM and phosphoric acid fuel cell efficiencies. When an SOFC is used as part of a CHP system, the CHP system can have an efficiency in the 60 to 80% range. Low-temperature fuel cells like PEM fuel cells cannot compete with high-temperature fuel cells like molten carbonate fuel cells or solid oxide fuel cells as stationary power plants as part of a CHP system. Conceivably, an SOFC CHP system could consist of an SOFC, a gas turbine, and a steam turbine. The SOFC could make electricity directly from the input of a natural gas. The hot exhaust from an SOFC could turn a gas turbine that is hooked to its own electric generator. The hot exhaust from the gas turbine would still be hot enough to boil water. The steam from the boiler could drive a steam turbine that could turn a second electric generator. In this SOFC hybrid gas turbine and steam turbine concept, we get 3 sources of electricity from one system. The flow diagram for this SOFC two-turbine concept is shown in the figure. I also show an SOFC turbine hybrid power plant built by Mitsubishi of Japan. A picture of a stationary SOFC power plant built by FuelCell Energy in Connecticut, USA. Lastly, I have a solid oxide fuel cell powered automobile built by Nissan in Brazil in 2016. This SOFC powered car runs on bioethanol produced in Brazil from locally grown sugarcane. Thank you for watching. If you enjoyed this video and want to help me make similar content, please like and subscribe.